So the topic, as Alessandro mentioned, it's a bit long, but I'll try to explain it as we go along. So the title of my presentation today would be Model-Driven Design Decision Support Systems for Complex Engineering Systems. I'll be focusing more on the challenges in the early design stages. So the agenda of the presentation would be that first we're going to go through the background, the motivation behind the research, then aims and the research question being put forward. To the audience, I'll discuss some basic important definitions that I'll be using throughout my methodology and results and conclusion section, so you know what I'm talking about. And then research methodology, results, conclusion, and then the overall outlook of the research. So let me start by telling why early stage decisions are so important. We look at different case studies. For example, here we look at Boeing 787 Dreamliner. So because of market competitiveness, they decided to have like a more efficient and like less, an aircraft which weighs less so that they have more fuel efficiency. So a decision was made to shift from aluminum-based materials to carbon fiber composites. But there was a consequence, a major weight reduction, 20%, which increased the fuel efficiency, 20%. But another consequence was that there was a huge supply chain disruption because more than 50 vendors were there in the supply chain, so they couldn't provide it. And resultingly, 3 years delay costing billions. So one decision has such a huge impact on the product itself. And then take another example. We all have seen that in pictures, like the famous Opera House in Sydney. So that building was approved before the engineering feasibility was conducted. What the consequence of that decision was that the cost inflated 14 times, from 7 million to 102 million, because they were not ready to make significant changes to the design. So the design impact a lot. So, and now when we look at the design paradox, so there is a problem when we are making early stage design decision. So we are here at the conceptual phase of the product development. We have very high design freedom, but we have very less knowledge about the design problem. So as we move along throughout the product development stage, the design freedom becomes less, but as the design knowledge increases. So we are here in a paradox situation, but we have to make decisions early on, and those decisions have very high impact, and those decisions are made in uncertainty, in uncertain situations. Why we have to make decisions early on? Because of the cost as well. So as early when we make decisions, there is less impact on cost. If we make those design decisions later on during the product life cycle, we incur more costs. So what would be the better scenario? We have higher knowledge. And higher knowledge means we have less uncertainty in making those design decisions. So ideally, we can have we have a situation where we have all the knowledge before we make a decision, but that never happens because a real world has always uncertainty which we cannot cater for. So how to have a better scenario then? We want to move from intuition-driven design decisions to evidence-supported decisions. For that, we need to have an understanding of system ripple effects before the freedom is lost. We need to have broader knowledge base. We want to have models that can actually forecast, and we need to have some kind of analysis, sensitivity analysis, for example, where we can see how those ripple changes affects the overall system. For that, when I sum it up, it means that we need to have some kind of a decision support systems, and we do have. So what's the decision support system? Decision support system is a socio-technical system. It has different components in it. Specifically, it has a model base where you have different simulation models in it. The dependency models, how each simulation models actually depend on each other and on different parameters. A knowledge base which shares the context of the information of the data, the database itself. On top of it, we have a graphical user interface where the decision makers can actually interact and utilize all those model base, knowledge base, and databases. And then we have a social aspect, which are users. So it's a combination of socio-technical system. But when we have socio-technical systems, we have challenges, right? So we have technical challenges and we have social challenges. So in this thesis, I have aimed to identify those challenges. I have primarily focused more on technical challenges rather than social challenges. I've just touched upon one social challenge, which is more like a usability aspect of the decision support system. So this motivates me to actually aim for this. And the aim that I put forward is to investigate the challenges encountered when using model-driven decision support systems in early design decision-making in complex engineering systems. So based on that, I put forward one research question to make it very simple. And it's a exploratory, descriptive and qualitative research question that what are the key challenges associated with current model-driven decision support systems? I'll be focusing on early stage design in complex engineering systems. So a bit of an important definitions. So I talk about complex engineering systems, right? So what are complex engineering systems? These are tightly coupled systems whose behavior are difficult to predict. And as far as its characteristics goes, it has a heterogeneity, which means it's multidisciplinary models or like system, which are interconnected to have an emergence. What is emergence? Emergence is like, for example, we have hourglass. You have a glass and we have a sand. When we combine together, we have time, for example, like the stopwatch. So this is the emergence. And when we talk about the system of systems, we also add a bit of layer of complexity where its constituent systems have managerial independence and geographical distribution. So I'm just gonna give a quick example. This is a complex engineering system. It has heterogeneity, different physical models, for example, mechanical, hydraulic, etc., interconnectivity. All the subsystems are interconnected. One change in one subsystem reflects the change in the other, and the emergence, the overall productivity. And then when we give an example of system of systems, for example, the same in a quarry, for example, where there are wheel loaders, crushers, haulers, all working together. Each of that subsystem has a managerial independence, yet they are geographically distributed. So it adds another layer of complexity. So this is where this is how we define system of systems. I mean, in literature, there are so many variants of system of systems, but basically everyone boils down to these characteristics. So now I'll move towards the methodology section. The research, what kind of a research methodology I have utilized in this research. I have used design research methodology by Blessings and Chakrabarty because I believe that in design science, it is one of the most relevant science research methodology, which has allowed me to move forward between different research clarification, descriptive study, and prescriptive studies. So within the framework of DRM, I applied participatory action research because I was working with two different case studies with industrial partners, namely Volvo and Mehdi Turku, which allowed me to include the industrial practitioners in my research, so I use participatory action research as well. As far as the research activities goes, paper A, which is included in the research, is based on a research clarification. It is a review-based clarification, and then same for the paper B, but it also adds another aspect of the descriptive study part, where it basically, the descriptive study means that it brings up the better understanding of the problem. The paper C is comprehensive descriptive study. It is the case study 1 with Volvo, and it also prescribed initial construct, which is, we call it like, it is basically initial prescriptive study, which means it provides some kind of support to the understanding we have developed earlier. And for the paper D, which is a second case study from Mehdi Turku, it's based on research clarification, descriptive study 1, and it also provides initial construct as an initial prescriptive study. So the case companies, I've mentioned 2. Paper C contains Volvo, where I have dealt with the wheel loader. So it is an off-road machinery with the high workload variability. It has fast repetitive cycles when we are dealing with quarry mining site. The uncertain factors are operational context variability. It requires real-time feedback with reduced computational cost when we are dealing with the decision support that it requires. As far as the data goes, for the customer part, it requires medium data, because it will just going to be using the data that we're providing, like the usage data, operational data. And for the provider, it will be high, because rich engineering simulations are being used in it. For the paper B, the case study number 2, it's a cruise ship manufacturer, Mehdi Turku, shipbuilding, high variety, low volume context. It has a long life cycle, the modular configurations. Uncertainty factors are newer modular design approaches. The decision support, what it requires was real-time feedback with a user-friendly environment to explore different trade-offs. As far as the customer data utilization code, it requires a lot of detailed specifications to be input into the system. And for the provider, it's medium, because we only give sustainability databases, which is supplemented by AI data. For the data collection, paper A is based on scoping review on meta models. So it's a review based, so all data comes from the literature. Same as goes with the paper B. It's the state-of-the-art review on decision support systems. For the paper C is the case study 1. The data comes from literature. Less data comes from literature and in unstructured interviews, and more data coming from the simulation itself. And for the paper D, the data comes from the literature, the unstructured interview, and the prototyping session or the workshops that was conducted in the premises of the company. So now I will go through the results. So the results are basically like those identification of the challenges, right? So just a brief intro to that, like the decision support system, as we have earlier said, is a socio-technical system, and the results focuses more on technical aspects, less on the social aspect. Specifically, less on, no emphasis was given on organizational integration or the adaptability aspect. So the first challenge, which was identified in paper C, is the lack of integration of heterogeneous simulation models. So we are in a scenario where simulation models, they are operating at different granularity. Some are at a higher fidelity models, such as discrete element method, and some are lower fidelity models, such as discrete event simulation. On the left side, you see particle-to-particle interaction simulations. These are very much detailed simulation, requires a lot of computational time and resources. So we had an innate need to actually have those two bridge together to have a decision support system for an operational context. So an initial construct was formed. I will call it an approach. So where we have discrete element model, the machine properties, particle properties, we ran a design of experiments and the integration of those simulations. And then we put all the data into the database. We created a surrogate model using LSTM machine learning technique to form basically an input-output relationship, basically like a surrogate for it. What it helped us to do is it allows us to utilize the discrete event simulation with it so that we can actually bridge the granularity gap between the two. Now we have a surrogate which we can run instantly without being like waiting for hours to do the particle simulations. So this was showcased in paper C, and that was also like the problem identified in the decision support systems. So, for example, when we dealt with that, I mean, just to give you an example, which kind of operational scenario decision making could be done utilizing that, we have three different scenarios. I'll just kind of focus on one because of the shortage of time. So, for example, in the second scenario, we have four haulers working into a pair of two with the different capacities. We see that even those upper results are from the wheel loader. So when we are increasing the bucket size, at some instant, we're not going to have more productivity, even though we are experiencing more energy, we are utilizing more energy. So there is like waste of energy, waste of resources. So this is how we can actually optimize the site, the query site. So these kind of operational decisions can be made with this approach. Another challenge that we found, I found in paper D, I saw a clear imbalance between different disciplines. For example, aerospace and automotive, they are way more mature than other, for example, maritime. Why? Because there are different factors. We see that in those specifically aerospace and automotive, there's a rush for new fast product development. They have shorter product development cycles, so they need to innovate. So the concept of like, the digital twin and all these kind of stuff are more prevalent in aerospace and automotive rather than in marine sector. And also we found out that the data availability is quite more in those disciplines rather than in maritime or other domains. And then with that, they are associated with, methodological factors are also associated because model-based systems engineering, for example, these kind of stuff are more prevalent in aerospace and automotive. And the technological ecosystem, for example, PLM systems, they are more aligned towards these rather than maritime. So, but it is gearing up, but still there is a gap that needs to be filled. Another challenge found that most of the time, the stakeholders, they are making decisions based on some decision support systems, and they are treating that as a black box. They don't know what kind of, for example, models are there, what kind of assumptions are there, what kind of dependencies are there. These kind of stuff, they really don't know because the system is just so close. But they are just trusting it as a black box and just utilizing it. So that's also like one of the challenge which I believe needs to be sorted out. So another thing is that we want decision support systems to act like a boundary object. What is a boundary object? Boundary object is a common reference point for different people from different backgrounds to interact and collaborate, negotiate, and align themselves. So specialist-only models basically hinders collaborative decision-making in such environments where multidisciplinary teams are working. And those hidden assumptions and embedded decision rules, they also reduce this transparency and the trust on the overall decision support system. There was an we saw there was a need when we were working on Mayor Turku project that sales and engineering teams, they used to they wanted to utilize a decision support system as a boundary object, where they both get the information from the same model yet for different purposes. So we created one where we use a model layer, a system. For example, we took a hotel subsystem as an example. Within itself, there are different subsystems. We created the model of all subsystems based on that material composition, the emission calculation models, and basically we put it into the database for the parametric emission model. The data layer, we have multiple sources of data coming from different, for example, the data from the user or from the database, emission database. And on top of all, there was a user interaction layer, which we called decision support environment, where initial thought was that, and is also that engineering and economic KPIs should be considered at par, and they could be visualized and compared against the baseline configuration, perform the analysis and make those decisions. So that actually allowed us to actually make a decision support system for sales and engineering team. We have yet to validate it, so it's just an initial construct. And another problem that was identified was that there's lack of metric to gauge the model maturity. Because in decision support systems, there are multiple computational models with variety of validation status and the data quality. So without maturity gauges, the decision makers might have lower confidence and less trust on those results. And some decisions may be biased toward a favorable looking outputs rather than, even if they are based on weak models. So what we want to do is we also want to have something that all technical stakeholders should not struggle to trust the decision support system. And they can do so by having some kind of a scale, model maturity scales, where they can trust the scale itself rather than the models which they are taking it as a black box. Some model maturity matrices does exist and they are implemented, but not widespreadly. So they still rely on expert judgments rather than some maturity matrix. And the sixth challenge that we found from the paper B was lack of life cycle management aspect. So when we progress toward the development cycle, we have more data, dependencies, and new roles and logic that has to be somehow imported in the decision support system. So it shall support we want to make decision support system as a living and evolving system. So we want to have some kind of a tracking and managing sub-model changes and dependencies, and version controlling, the configuration management, and we shall have something like it should flag when affected by model updates, and there should be transparency on model origin and validation. Oh, and there is another aspect when I was dealing with the heterogeneous simulation models. So there was a lack of semantic clarification for the term meta model. So there was I saw the need to actually have some kind of a literature review to highlight what kind of interpretations are there regarding meta models in different application areas. So a scoping review on meta model was performed in paper A. We found out that in two different domains, like systems engineering and in computational engineering, the definition is used or interpreted differently. So in systems engineering, the meta model is considered as a framework for building other models, and which ensures standardization. It always operates on a higher level, and it offers guidance to creating other models. But when we consider the definition in computational engineering, it acts as a surrogate, and the purpose is to have a reduced computational complexity and resources, and it always operates at the lower abstraction level, and uh, provides the basic approximate predictions, enabling quick assessments. So in conclusion, so addressing a research question. So the question was simple, like, what are the key challenges associated with it? So I have listed those challenges here as I have explained it before. So I'm not gonna go through them again, but the general thing was that I was able to identify the challenges, and also I was able to develop initial constructs to have some kind of problem solving thing as well. So the basic outlook of the research is, in near future, I would like to have do application of those approaches to the broader set of design studies, and validate those initial prescriptive constructs, formulation of some kind of a formalized framework, and then apply those framework in an industry in a distant future. So I would like to thank my industrial partners, Turku and Volvo, and I also would like to thank Vinova for providing the financial support. I thank you all for listening to my presentation. Thank you.